We can call it a current controlled current source. It means the value of this output current will be depending on this input current. Why? Because for a particular AC VBE, a particular amount of AC current will be injected into the base, right? And that amount of that will control the amount of the AC collector current, right? Because these are interdependent, right? So if these are interdependent too, so we can say that these two are also interdependent. So GM is transconductance of the controlled source, right? So whatever VBE you have, it is multiplied with the transconductance to get the value of this IC, right? Or when you have a VBE, you can easily find the IB, and beta time of this IB is your collector current, right? So collector become the current source for a common emitter based amplifier, right? And amount of that collector current source will be depending on voltage at the base to emitter junction. So it can be called as voltage control current source multiplied by the transconductance, value of which will be highly dependent on the quiescent value of the bias transistor. Or you can say that this is a current source controlled by this base current, right? One more thing, that the output resistance of the control current source is infinite, right? So if this is the source, right, then it has no output resistance here. Practically, we are always have an output resistor for current source. The output resistance is always parallel to the source. Then you can place your load, and for a DC voltage source, you would be having a series output resistance with that source, right? So we don't have it. Why? Because we have neglected the early effect. So it means we took the ideal case for the collector to base relation. That's why we are actually come at the point at which we have a small signal model of this transistor in the form of having an ideal collector current source, right? If we would have taken the early effect here instead of neglecting it, we would be having a current source with a output resistance here, right? So base current and input resistance at the base, right? We have seen that we can make a small signal AC schematic of a transistor like this instead of this, right? For AC equivalent circuit. So we have a VBE, AC VBE developed across base to emitter junction, right? Terminals, for which this base current enter into the base of this transistor, right? This blue shade tells you inside, modeled inside of this transistor, right? So if for a current, for a voltage, and for a linear relation of current and voltage, we already have a linear relation, right? For a small signal, we would be having here what? Let's see. We know that for a total collector current divided by beta, we can have a total base current, right? And we already derived for small signals that total collector current is nothing but the sum of DC current and the AC current, right? And we have named this IC by Vt constant value as Gm for a particular Q point, right? So how about IB? We know that IC by beta, so we can divide this relation or this relation as well. So if we divide this relation, we are having this value, or this one is the same, right? IC by Vt is Gm. You can have this value or this value, right? So it means your DC total base current is also DC base current and AC base current. So DC base current would be totally dependent on your DC biasing. So is derived here, right? DC collector current divided by beta. So would be your AC base current will be dependent on the AC value, right? So it's depending on AC VBE. Of course, about DC biasing, right? So, or instead of IC by VT, you can write GM by beta. GM. So you will be having a relation of GM by beta into VBE, right? So IB is equal to IC by beta VT. You can take this one or this one. It's up to you, right? It's the same because IC by VT is GM. And we know that within a junction, if you have a voltage across an electronic component and a current of this relation, V is equal to IR is nothing but the Ohm law, right? So V upon I is nothing but resistance. So if you have modeled this transistor as this small signal model, and this electronic component would be having current inside going inside and having a voltage across this thing and related linearly to each other, then they would be nothing but a resistor, right? So we can name this either RP because we are looking into the base, right? Or R pi. Why pi? Because of the name of this model. We will see it later how we define the name of this model, right? So R pi or RB, and it will be equal to VBE by IB, right? So here VBE by IB is nothing but beta BT by IC, or VB by IB is equal to beta by GM. Same, right? So this will be your R pi, or IC, if you put beta here, IC by beta is nothing but IB. So very simple to be memorized, right? R pi is equal to VT by what is IB, the base biasing current, right? So this also proves that your AC collector to base to emitter voltage, which needs to be amplified, will be depending highly on your biasing as well, right? So this resistance at which this base to emitter voltage will be developed out of this input voltage, because out of this input voltage will be some part of this will be VBE, and how much it would be, the value of this resistor will define. If this resistance is large, this will take more contribution from this input, and it can then be multiplied with GM to have a more current. So it means it's totally depending on your biasing as well, right? So, but remember, we have a base to emitter junction as an input, and we have because we are looking at the base to see into the transistor. So this resistor is actually at the base side, although it is in between base and emitter, but it is not here at the emitter side, it is here at the base side. So it means whenever you are modeling the transistor with a small signal model but looking into the base, at base you have a resistor at base, right, instead of emitter. We will see how we can write, we can also model the transistor by looking into the emitter. So this is the model shown for voltage controlled current source. This current source is controlled by this voltage, right? And of course your biased transconductance value, biased, right? Or instead of writing this, we can also have a relation with this one, right? Same thing, but we can write a relation here. Instead of GMBB, we can write beta IB because these are interdependent. So we can write this dependence of this directly with the dependence of this, right? So beta IB. So we can say this is a current source controlled by this current. This is a current source controlled by this voltage. The voltage controlled current source, current controlled current source is the same. So these two are exactly the same, relating different variables for different purposes, right? So let's go further. The emitter current and the input resistance at the emitter. We have a model, small signal model of this transistor. Previously we looked into the base and see how it is taking the current and having voltages. So now let's see if we are going to see into the emitter what we can see. So we have an emitter relation, emitter current relation with the collector current is with IC by alpha, right? So we already derived IC, right? So we will follow the same steps as previously for base current. So again IE is equal to IC by alpha. So divide this equation by alpha, you can get this, or this instead of IC by VT you can follow GM. And again total emitter current is nothing but the DC collector, DC emitter, those are emitter current is nothing but DC emitter current and AC emitter current, right? So DC emitter current is this one, AC emitter current is this one. Or instead of writing this you can write GM. So DC collector current remains the same, while AC emitter current can have a relation of this kind as well, because these two are equal. So it means AC emitter current, the current topic of discussion for AC modeling for small signals. We are having correct emitter current like this, right? Again, it is totally depending on this VBE, right? And this would be constant for a constant for a bias transistor, right? So instead of IC by VT, you can write GM, right? Again, looking into the emitter, if you are having a voltage and you are having a current out of or into, for NPN it would be out of the emitter, for PNP it would be into the emitter. So into the terminal and a voltage across that terminal about some other terminal, you have a resistor actually. That component can be modeled as a resistor. So it means by looking into the emitter, if you want to model this transistor for a small signal, but looking into the emitter, you can write the model like this. You can make the model like this. Please don't be panic. We will compare both the models and then we will see there is nothing difference, no difference between these two models, right? The only thing how you consider for your application, right? So here, if you look into this emitter, right, you can see a voltage is developing here and a current is going out for NPN, right? For PNP it would be in. So it means you would be having a resistor here. So again we have an emitter between base to emitter, but at this time not at the base side but at the emitter side. So same, you have a current source at the collector side, right? If you are confused with this node, forget about this, because this is not a short circuit connection.